K-map.
Okay, let's start. So, what is a C compiler? A compiler is a program that reads a file in one language, translates them, and outputs files in another language. So, it is a type of translator. For example, for C language, we have MinGW compiler in Windows and GCC for Linux. It is platform dependent. It is achieved by a practical implementation of grammar rules that we have studied in theory of computation. You must have seen that we compile a C program using commands like gcc hello.c. This produces an object code called a.out, which is an executable file. So in this case, GCC is the compiler to compile C language code. In fact, the entire Linux operating system was compiled using the GCC compiler. You can implement a compiler in any language, including the same language that it compiles. This is called self-hosting. So a compiler for, say, language X can be written in X language itself. Okay, so let's talk about the prerequisites first. Knowledge of theory of computation and the grammar rules is required. If you have never studied theory of computation and you have time, so then I'll leave Amit Khuranna sir's lectures links in the description. The course is quite long though, but it is worth it as it builds a very strong theoretical CS foundation. If you are short on time, then you can pick up any gate lectures on TOC and study from it. Another thing is you need a basic understanding of C language. For that, I will again put a link in the description for Amit Khurana sir's C lectures. We will use C because it is the perfect language for understanding how an implementation really works, all the way down to the bytes in the memory. So, why are we building this? Implementing a language is a real test of programming skill. The code is complex and performance is critical. You must master recursion, dynamic arrays, trees, graphs, and hash tables. I remember when we had paper on compiler design in fifth semester, and the terror we felt. It was one of the most daunting subjects for us in CS. But even then, I felt that most of the fear was there because we didn't really understand the application of it. Sure, it converts source code into an executable binary file or bytecode, but how does that exactly happen? If the theory was taught with proper supplemented actual code, and we built our own compiler in stages, it would do a far better job than cramming the different stages of compilation and the grammar rules. One more reason why I used to find the subject scary is because we look too closely at the picture. We focus too much on cramming the rules of the different parsers before even understanding what they're actually doing and what is the shortcoming of each one. To understand something properly, we first need to look at the full picture. Therefore, we will have an overview of the different stages of a compiler. It will show you what actually happens to a code file when you save it as hello.c and compile it. What are the different stages it goes through? Later, I will also add theory to it and some pen and paper based problem solving so that this lecture is useful for college CS students. I don't want you to think of the compiler theory and practical coding of it differently. The foundations for both will be built simultaneously. We will be using an evolutionary model for building the compiler such that from the very first segment, you will have a working program you can run. With each passing segment, it will increase in features until we eventually have a complete language. I will try to keep the program in a runnable state even when the major features are missing. Sometimes we add temporary code late that gets replaced later. Okay, so first let's talk about the different stages a program goes through in a C compiler, like say the GCC. First stage is pre-processing. In pre-processing, we handle macros and header file inclusions, like the hash include stdio.h, or the macros such as hash define, suppose pi space 3.14, which gives a value of pi 3.14 before even compiling it. This is a part of pre-processing. So these include the headers and also the macros. After that comes compilation. We see that compilation itself is just one stage out of five others in the whole process. In this stage, the C code is converted into assembly code. Assembly code is platform dependent, as Intel and AMD or Raspberry Pi will have different assembly codes. Compiler is also in charge of throwing warnings and errors. The next stage is assembler. The assembler converts assembly code into machine level language or object code, such as this. Then comes the linker. Linker links the required library files, suppose this and this, which are already compiled and present as .dll in a Windows machine. Then comes the last stage, which is the loader. The loader takes the object files from the disk and loads it into memory. This has more to do with the OS than compiler. After that, control is again given to the OS to start executing it. Notice that compilation and assembler are different stages, but mostly when we say compiler, we include both of them in it. Now we are going to go through all the phases of a compiler and give you a brief overview. Then we will pick up each phase and study its theory extensively. So first have a look at the different stages. This is just the overview. This is the first is the lexical analyzer, takes the raw input, converts it into a set of tokens. Then the syntax analyzer, using a grammar, a context-free grammar, converts it into a parse tree. Then there's the semantic analysis phase, which handles semantic errors. Then the intermediate code generation, which converts it into three three form code, three address code. Then code optimization, if there's any optimizations which can be made, then both machine independent and machine dependent optimizations are made. Then the code is generated, and finally assembly code is generated. So now we will just briefly look at each stage. After that, we will study each stage extensively. Okay, so the first stage is called scanning, also known as lexical analysis. A scanner reads a linear stream of characters from left to right and chunks them together into a series of tokens. This entire each thing is called a token, and all of them together are called a series of tokens or a sequence of tokens. A lexical analyzer is nothing but a finite automaton at its core, which you will learn in theory of computation. I will seriously recommend you that you watch theory of computation first and then come here. Then you will be able to enjoy the subject more. In fact, I feel like people should be told what theory of computation is mainly used for. Then it's more fun to study it. Otherwise, you don't realize why you're studying theory of computation until it's too late and you already have compiler design in the next semester. Anyway, this phase just checks if the user input is uses correct words or not. For example, instead of int, if I had put itn by mistake, then it will not be able to convert it to a proper token, and thus it will throw an error. So these tokens represent like words. So int is a keyword, so kw keyword. I've not written the full thing, I've written smaller a. Then x is an identifier, id. If there was another y, suppose 10 plus y, then we would put another id here. Okay, then equals to is equal operator. Then there's a 10 which is constant, and then there's the end of sentence operator, which you can write as eos, or I've written as this only because it's just a symbol. Okay, now the next stage. I'll go over each of these stages in a lot of depth and we'll solve problems later on. I just want to give you an overview right now. In the next stage, the input is a set of tokens. Okay, so I've shown you this again. I've shown you that lexical analyzer. This is another statement. I've written x equals to a plus b. Lexical analyzer converts it into tokens. See id, that means identifier. X is identifier. Equal operator. Then a is again identifier. Then plus is an operator, just a normal operator, not equal operator. And b is another identifier. And then there's the end of sentence symbol. Okay, so this entire thing, let's consider it a word, a set of tokens. This is then passed on to the syntax analyzer or the parser. So in this next stage, the input is a set of tokens. The syntax analyzer generates a parse tree. This is the parse tree, and checks if the word means this thing, belongs to the grammar using context-free grammar. So basically, you'll understand it if you have studied theory of computation. This is the grammar. It already has a grammar put into it, the syntax analyzer, and it checks basically that using this grammar, can you generate this sequence or token, which let's call it a word. So using this grammar, can we generate this word? And this is just a pictorial representation of that. The parse tree is used to generate this word. You see, from s we get the id, the equal operator, and the non-terminal capital A. From that capital A non-terminal, we get id, operator, and id again, and the end of statement operator symbol also. So from this you can see, if you have a pre-order or in order, no sorry, if you traverse it in a pre-order fashion, you will see that you can generate this word. So that is how you know. So the entire point of this is to check if this word belongs to this grammar, or if this grammar can generate this word. It's checking if the word if the word is present in the language which is generated by this grammar. So what kind of errors does the parser check? Basically, for example, if I write int 10 equals to x, int 10 equals to x by mistake, here we see that there is no issue in the words itself, because int is fine, 10 is a constant, equals to is fine, x is fine, end of statement operator is also fine, and thus it will therefore it will not be caught by the scanner or the lexical analyzer. It will be converted to a set of tokens, like keyword, constant, operator, id, and eos. The parser will check if the sequence of tokens belong to the language generated by the grammar g. Like this belongs to the language generated by this grammar g, but in the int 10 equals to x1, I have not written it down. It will see that that the word cannot be generated by that grammar, and thus if not, it will show a syntax error. So that is all. Again, there are more data structures that are created and used during scanning and parsing, but we will study them when we study each phase in depth. The whole point of this is to create a mind map in your head of how the entire thing works. Don't worry if you are having trouble with tokens or converting it to a parse tree, because we will revisit it later and solve a lot of problems on it. I just want to form a map in your head. That's all. Okay, so I want you to take a look at the code here. We see that this is syntactically correct, because this is an integer variable declared, boolean variable declared, and char variable declared, and they are initialized. Then they are adding x equals to b plus c. You might think that you might see what's wrong here, that you are adding b, which is a boolean variable, and c, which is a character. Let's assume that this will get converted into its ASCII value. Still, it is not compatible, but syntactically there's nothing wrong here. So the lexical analyzer will not show any error. The syntax analyzer will also yes, the parser will also not show any error. So we need, in the third stage, we are going to do semantic analysis. We basically check the data types and if it is compatible. We perform data type conversions. If it is compatible, then we perform data type conversions. We check if the variable is even declared at all or missing. We do this using a syntax directed tree. After the command is given, it generates a syntax directed tree, and from there it can judge whether there is a semantic error or if it is fine. If it is fine, then it moves on to the next stage. We will study syntax directed tree later, and then we'll see how exactly this works. The next stage is the intermediate code generation. You can see that there was a line of code here, and it gets generated into this. Intermediate code means 3 address code. You will see that there are only 3 variables here. So 3 address. It is generated to make the next phase easier. So you can see that this is broken down into in such a way that in one command or in one instruction, there's only 3 addresses present. Okay, now the next stage is very important. It's called code optimization. The entire goal of this stage is to reduce the number of instructions in the code without changing the output which is generated. There are two kinds of optimization. There's machine independent optimization and machine dependent optimization. This is a case of machine independent optimization called short circuiting. We know that the value of anything odd with 1 is always 1. So why bother performing the operation when we can save CPU cycles? This will take a CPU cycle to perform. So why bother doing it? So we can directly write it as int x equals to 1. This happens in the machine independent optimization, because this will happen regardless of what kind of processor we are using. In every kind of processor, if we do this is an optimization. That is why it is called machine independent optimization. There's others like it, such as folding, strength reduction, redundancy removal. We'll study them in detail later. Then there's the machine dependent optimization. That are basically optimizations made for particular microprocessor architectures. This includes register allocation and peephole optimization, which sounds wrong, but it's a real thing. That's right. We will study it in detail later. Okay, so From the scanning till machine independent code optimization is called the front end of a compiler. And from machine dependent till the next stage, which is called the last stage, code generation, is called the back end of a compiler. So basically, the front end is machine independent. It doesn't matter. Suppose I was making a compiler for the C language on a Raspberry Pi, then the front end of the compiler will work on a Raspberry Pi as well as some other microprocessor, let's say AMD microprocessor, or there's thousands of others, I don't know. But the machine dependent part, which is the machine dependent optimization and the code generation part, will be different because assembly code for each microprocessor is different. Finally, we come to the last stage, which is code generation. Here we get the assembly code, which is different for different microprocessors, as I said. The assembly instructions are used to perform data transfer at a register level. So this is the CPU. You must have studied this in computer architecture. This is the CPU. Inside the CPU, there is the ALU, arithmetic and logical unit, inside which there are registers which are used to which are used to hold values uh, instantaneously, on which the ALU is performing operations on. So momentarily, they hold values. So these are registers. I have named them R0, R1, and R2. And so the assembly code are used to perform data transfer at a register level and perform arithmetic operations at a register level. Now, before I end it, I want to tell you the difference between a compiler and an interpreter. Because knowing the difference is critical to know what we are building, and it is also asked in most interviews. In interpreters, the code is executed line by line. The code is not precompiled. So, in case a syntax error does occur, it becomes difficult to undo the previous commands. A few examples are SQL, and then there's Lisp. And a compiler basically compiles the code all at once and generates an object file. A pure example would be C language. There's others. I didn't research that much. Let's list down the differences. Basically, in interpreters, the code is executed line by line, as I said. Interpreter codes run slower because it is running each instruction when we are like when we are running the code. When we have executed the file, then it is running the code line by line. So of course it's slower because compiler has already done that work. It has compiled the entire thing. Now it's just executing the instructions. But the interpreter has to first decode the code, understand the code, then it executes. The interpreted code does not save the machine language. Of course, it does not have an object file that it saves. It requires the source code for later execution. Yes, it does. The compiler once in a compiled language, once we have suppose we had a file called hello.c. I've compiled it and saved it. I've compiled it and it generates a file called a.out. I don't need the original source file. I can just take the executable file with me and run it. Okay. Now, there's a common misconception. Java and Python are not purely interpreted languages, as most sites say. They're hybrid. Instead of choosing one method, they use both. They are both interpreted and compiled. They first compile your code into an intermediate format, which is called bytecode, and then they interpret the bytecode. So it is hybrid. So that is it for now. This was just an overview to tell you how the entire workflow happens. In the next videos, we will take each phase and study it in detail. Along with the theory, we will simultaneously build our own compiler. Thank you.
K-map